Yeah. Welcome back, everybody, to this new session of the Chilean Probability Seminar. We have the pleasure to have with us Nicolás Zalduendo, an old friend of the seminar, and now a member of CMM. He's a postdoc working here. So he will discuss about central limit theorems for structured branching processes.
Thank you very much for the introduction and the invitation. It's really nice to be back. So for this talk, I'm gonna discuss a little bit about branching process. But if you've never heard what a branching process is, or if you have and you're a little rusty, I will start by explaining what a branching process is. And the central limit theorem part of the title hints at I'm going to study fluctuations of a process, and I hope that these fluctuations are Gaussian fluctuations, okay? So why study branching processes? The goal is to study, to model the evolution of a population. So for instance, you can think of a bacteria, you have a petri dish and a bacteria that is going to reproduce, is going to divide. And so you look at a certain time at the beginning, and then sometime later, this bacteria has divided multiple times. And if you look again, it has a large number of descendants. Another idea we can say to model, we can try to model the propagation of a virus within a population. So you can think that you have two types of individuals, the individuals that are infected and those that are not infected, and you want to model the spread of the virus within this population. Or for instance, imagine you just want to model your population is just a bisexual population that can reproduce. So I'm going to start with the basics. So I'm going to work on continuous time Galton-Watson process. So imagine your process that models this population evolves as follows. So you start with only one individual at time 0. And this individual will have a lifespan, and we want this process to be Markovian. So the life of this individual will be an exponential random variable of a certain rate lambda. And after this lifetime, the individual will die and will be replaced by its descendants. And the number of individuals of the descendants will be a random variable, a certain law, and I will call X the random variable with this. I'm going to assume that this reproduction law has first and second moments. And then the new individuals that are created will evolve in the same, following the same dynamics. They're independent and they will die at rate lambda, and once they die, they're replaced by a certain number of individuals, which is an independent copy of this random variable. So to give you an idea, at time 0 in this process, if I look at time to your right, then at time 0 I have just one individual, and if I denote set t the numbers of individuals that are alive in the population at time t, well, at this time t I just have one individual. So let's say it dies and it's replaced by 3 individuals. And so at this time I have 3 individuals in the population. At a certain point, this individual dies and it's replaced by 0 individuals. So I can think of no progeny in this case. And so later I have only 2 individuals. And then this one reproduces and gives 2. And I can go on and on. So this process that looks at the numbers of individuals at time t is what's called the continuous time Galton-Watson process. Okay? So first, this process can be extinct if, as in this case, I allow the individuals to have no descendants. The process can be extinct. So at a certain point, I can have 0 individuals. And so under which conditions this process can survive indefinitely. So what you can do is, if you compute the expectation of this process, so the expected number of individuals at time t, you can prove that this is just exponential, e to the power of lambda t, where lambda is a parameter that can be computed. Sorry, did I call lambda this? No, the rate is alpha. So it's computed using the rate at which each individual dies and the mean of this random variable x. So with that, you can separate in 3 cases. If this is positive, this mean is growing exponentially fast. So the idea is that in this case, the process can survive with positive probability. But in the cases where lambda is equal to 0, where your expectation is bounded, or lambda is negative when this is decreasing, your population goes to 0 almost surely. So we're going to focus on the case where you have a positive probability of survival, and in that case, you say that you're in the supercritical case. So first, if you divide this process by its expectation at time t, what you obtain is a positive martingale. And since we assume second moments, we have a square integrable martingale. And thus it is convergent to some random variable w. And this convergence, in this case, since I have a second moment, it's an O2 and almost sure. Okay? So our question is, what can we say about the fluctuations of this martingale here around its limit? So a first central limit theorem in this case, I mean the supercritical case. So if I divide, yeah, I know that the exponential, exponential of minus lambda t times my process is convergence to w. But if I take this and I divide by the exponential lambda t over 2, then this will converge to a center Gaussian random variable. So mean 0 and variance. No, it's a central Gaussian random variable, so it means it's 0. So the idea here is, when I look at this process, let me show you the drawing. Each of these individuals, it's behaving independently. So if I have a large number of individuals, all their descendants behave independently. So this process should look like a sum of IID random variables. So the fluctuations, I should rescale by the square root of the population to get a central limit term. That's the intuition. And that one can prove that is just exponential lambda t over 2. So a big limitation of this process is I assume that all individuals are identical. So what happens if I don't want that? So a first idea is, okay, let's say that I have a finite different number of types of individuals. So I'm going to fix D, and I'm going to assume that each individual can have a trait. So each individual has a trait, and this I have D possible traits. So what I do here is, I imagine for D equal 3, that I have 3 types of individuals, blue, yellow, and red, and now their lifespan depends on their type, and the reproduction law depends on their type also. But the idea is the same. Each individual reproduces independently with respect to others. So what I can do now is, in the general setting, I have a process in dimension D, where, should I go?
Yeah.
So CT1, it's the number of individuals at time t of trait 1, etc. And so if I look now at the expectation, but the expectation now I compute it as a matrix. This is a vector process, so I'm gonna take the inner product with a vector x. Now this is a linear operation, right? So I can write it as a matrix times x. And so one can prove that this is just, I can write it as exponential t of a matrix A. So it is the generator of the matrix M. And the idea is similar to what we do in the single type case, when we have no traits. So under good assumptions on A that I will not go into details right now, the largest eigenvalue of A will determine the asymptotic behavior of the process. So again, if this is positive, the process will have a positive probability of survival, and if it's 0 or negative, the process will be almost surely extinct eventually. So what we can prove is that, again, if I take my process, this is a vector process, right? And I rescale by the exponential of lambda t. Again, this converges to a certain random variable. And the idea here is that this process is stabilizing. And the limit direction of the process given by this vector z is the eigenvector associated with the eigenvalue lambda.
Just sure. So each individual will reproduce to some kind of this. Well, how will one individual decide to transform himself?
So you can think that each individual has a trait. This is a color in the drawing, and it has a reproduction law.
Okay, so
And the law depends on its trait. So a yellow individual will give birth to a certain number of individuals of each type, but the law depends on the fact that the individual is yellow.
Okay,
Yeah?
and that gives a matrix.
Yeah, the matrix with all the possible expectations. That gives a matrix.
Okay.
And I say, well, the eigenvalues of this matrix are of the time t are of the form exponential lambda t. And I look at the largest eigenvalue.
Yes.
I need some extra hypothesis to assume that I have a unique principal eigenvalue, the largest eigenvalue, etc. But if I divide by this quantity, so the largest eigenvalue of m, this converts to something that has the direction of the eigenvector.
Okay.
What you can think is that if I normalize this vector, the proportion of each individual is convergent to the components of the vector z. So what about the fluctuations? The idea here is actually, if I take the inner product with z, so I project over the first eigenspace, then this will converge to W. That's the idea. And you prove then that the other directions don't play any role, because everything is going to the direction of z. So what about the fluctuations of this object around this limit? So I'm going to just give an idea of what you can do, because then I will talk about structure branching process. There is a more general version of this model, and then I will give more details about this idea. But this is the way Atreya and Ney for the first article prove it in 71 and 72. And that is, okay, I have a matrix. So let's say it's diagonalizable, or I can take its Jordan canonical form. So I can found a basis of eigenvectors, of generalized eigenvectors for M, and I decompose all my space in this eigenbasis. So what I do is I will decompose this process by projecting over all the eigenvectors. And then I will see the fluctuations of the projection of this process against each eigenvector. And I want to decide if the fluctuations of that limit are Gaussian or not. So if I project over the principal eigenvector, when you do that, you obtain a martingale. And so you can prove that it has Gaussian fluctuations. So it's the same result as in the unidimensional case, only that you have only one direction there, so you don't see it as a projection. But then what happens if I take this process and I project it over a different eigenspace that is not the principal eigenspace? The problem is, I know this process is converging to the direction of z, and it's fluctuating around its limit. So I need to compare how compare the speed of convergence towards the direction z and the speed of the fluctuations in the other directions. So what happens is, depending on the eigenspace that I'm looking at, I have three different regimes. Two of these regimes are Gaussian fluctuations, and a third regime is not Gaussian. And each regime depends on the eigenvalue that I'm looking at, the distance between the eigenvalue that I'm looking at and the principal eigenvalue. I'm going to give more details on what I'm trying to do here, but for that, I prefer to do it in the more general setting. So I will introduce a structure branching process first. So the idea for structure branching process in the previous model, you're allowed your population to have D different traits. So imagine that D is not enough. You want an infinite number of traits. Moreover, you want a continuum number of traits. So what you're going to do is you have space states. Usually what you can think of R or R plus. And this will represent the different traits for your population. You can think, for instance, that your trait is your age or your position on space or something like that. Okay? So each individual has a trait. And what I'm going to do is I'm going to start with just one individual, and its trait is some point in the space, x0. And this, since I'm going to think that I'm in a continuum, I'm going to leave the trait evolve. So imagine that this trait of the individual can evolve following a Markovian dynamics that you know. So you can think that the trait is a Brown motion or a diffusion, or you can think that it's just a deterministic evolution. Okay? At a certain time, random time, where the time depends on the current rate infinitesimally, depends on the current trait of the individual is going to die. And then it's going to be replaced by a random number of new individuals. Now these new individuals are independent, and they behave similarly. So they have a certain trait. Their trait is gonna evolve at a certain time. Let's say that the upper individual dies and he's replaced by 2 individuals. At a certain time, another individual dies, but he can have 0 individuals, so you can have death. Or the reproduction can be non-local, meaning that the new individuals have not the same trait as their parent at the moment that they die. So you can think of a lot of generalizations. And what we're going to do is I have a continuum of traits. To represent this process, what I'm going to do is I'm going to put Dirac masses on each trait of each individual at time t. So what I'm looking actually is points that are moving according to a Markovian dynamics X. And at a certain random point, these masses split and give new masses, and they continue to evolve. So at any time t, if I call nt the number of individuals, the set of all the individuals that are alive at time t, then this process can be defined just as a random point measure.
Does reproduction law depend on the trait?
Yeah, on the trait, at the moment of the reproduction, yeah.
Okay.
It's clear how the process works. So I can give you some examples. So a classic model is growth fragmentation. So I'm gonna imagine that I have a cell or a bacteria, but that can grow. So they have a certain size. I'm gonna start with a single cell of size 1, and the size is gonna grow exponentially. So this is the size of a cell. At a certain time, this is gonna split, and it's gonna divide its mass between let's say 2 individuals. So I'm gonna give 2 individuals here and here, and it's gonna be divided uniformly between the 2. So this is a uniform random variable, and they're gonna keep evolving. And at a certain time, this is gonna divide. It's gonna give 2 new cells that are gonna grow. So we have growth of cells and fragmentation when they die and they divide by 2. Yeah. So this is a classic example of non-local reproduction, because the trait that is their size is not a new cell is not the same as their parent at the moment they die, and the evolution is deterministic of each individual. So it's a piecewise deterministic Markov process. Branching Brown motion. So if I think that each individual evolves as a Brown motion, it's a really well-studied process. It's related to the solution of the FKPP equation. Or epidemic models, where I can think that each individual, I have 2 types of individuals, healthy or not, and the virus is spreading on the population, and the trait is the viral load of an individual. So I can determine how many people it can infect depending on the viral load. So what I show you in the d-dimensional case is that we look at the expectation. In the other case, also in the unidimensional case, and I want to do the same for this process. So what I'm going to do, this is a random point measure, right, in the space state. So what I'm going to do is I want to test it against functions. So I'm going to write st of f, the integral with respect to this random measure, but it's a point measure, so it's just I look at all the individuals at time t, I take f or all the traits and I add them up. I'm not going to say, you can think as bounded functions for the moment. I'm going to say later what are my set of functions that I'm interested in. But with that, I can define the mean semigroup just at looking at this integral and take the expectation. So this will form a PT, a non-conservative linear semigroup, meaning that its mass is not constant. So it's changing. If I integrate PT against 1, what I obtain is the number of individuals at time t. So what is the goal? Since what I did in the Inspire, what you can do in the finite dimensional case with D traits, if you look at the limit behavior of this matrix given by its principal eigenvalue will tell you something on the process. So let's study what are the stability properties of this semigroup, and let's hope that we can say something about the properties, the syntactic properties of this process, given this stability properties of P. Okay? the technique that I'm going to use is what's called a Foster-Lyapunov criteria. It was developed really early in the 30s by Dublin. Then Harris took over a theorem course also, and developed mainly for conservative semigroups. So in the last decades, mainly in the 90s with Main and Tweedy, and especially in the last years, Champagnat-Monet or Dansai, Chloé, Gabriel, Marguet, developed stability techniques for non-conservative semigroups. So what is this technique? The idea is, the most important hypothesis that you need to verify is the existence of what I call a Lyapunov type function. And what does this means is that I'm gonna find a function defined on X. So I'm gonna think of R that is go infinity in infinity. So it's a coercive function. So you can think of that function. And satisfies a drift condition. When I look at the infinitesimal generator of my semigroup, I have this drift condition here. What this is saying is, so this function is going to infinity. You can think of this as the derivative of your semigroup, right? So this is like going back because the derivative is bounded by minus alpha b outside a compact and plus a constant within the compact set. The intuition here is that your process, when you integrate it with respect to this Lyapunov function, I didn't say, but it needs to be positive. It can now is not escape towards infinity. So the idea is that this process here, when I integrate this with respect to v, this is gonna come back to your compact set. What is the good thing? You're working on a compact set, so now you can use classic techniques to study the stability of your process, but within this compact set, because your process is coming back because it cannot escape. When this escape, this drift condition brings you back. That's the idea. So again, now I'm gonna say, okay, this is the set of functions that I'm gonna be working on. So I'm gonna, let's say that I can find a Lyapunov function v, and I'm gonna work with all these functions that are bounded by v. Okay. And you can do is prove with this Foster-Lyapunov criteria, you have certain hypotheses on these functions, that you have stability of your semigroup, meaning that if you rescale your semigroup at rate lambda, then this is gonna converge to an object that it's decomposed as an integral of the test function and a function of your initial position. What is happening here is that this is a kind of, for those of you who know this term, this performance term. So what I'm saying is you can use this to prove that actually this is your eigenfunction. Exponential lambda t is your principal eigenvalue for your semigroup. Your measure gamma is your eigenmeasure associated to this eigenvalue, and this is your principal eigenvalue within this set of bounded functions. So the idea is you can prove that you have a principal eigenvalue like in the finite dimensional case, and if you rescale at that rate, you have convergence, so you have stability of your semigroup. Okay, and the limit, you know it, is you integrate with respect to gamma times h of x. So this is what I'm.
The framework for PDT is PDT must satisfy.
Yeah, of course, there are a lot of hypotheses that I didn't put behind. You can ask, for example, for irreducibility and a periodicity.
Okay.
But the main hypothesis that is the Lyapunov criteria for V plus the Bruching coefficient or Harnack inequalities. The idea is that PT is such that if you are in the compact sets, you can work the stability of yours. So the Lyapunov criteria sends you back to work compact sets. Okay, so I have a principal eigenvalue associated with a unique eigenfunction, a unique eigenmeasure as a positive eigenvalue, and I have stability. So what I'm going to try to do is, using the stability, what can I say about the process? So I'm going to suppose that I have a second, that should be set the integral against V, right? I have a second moment for my processes, I'm gonna do everything in this space of bounded functions of, by B. I'm just gonna ask that I can start my process integrated against B, and I can bound the second moment up to a certain T0. So if you, this of course is expectation starting from X. So if you want this function that a certain X associates this expectation, I start with just one individual of trait X. So this is bounded by it. That's what I'm asking. So what can I do is actually I can show that if I take my process integrated with some test function, that it's bounded by V. Again, I rescale by the eigenvalue as in the finite dimensional case. Then I converge to something that depends on the eigenmeasure. This is set in the finite dimensional case, times a random variable, and I can prove this convergence in L2, I'm almost sure. This is not a new result. There's a lot of papers working on that, papers of Andreas Cipriano, Emma Horton, Biggins, I think I have some results on this also. But
in the 80s or 90s.
yeah, a long time ago, yeah.
No, Emma Horton more.
Anche Cipriano more recently.
Yeah, but Higgins.
Biggins in the 90s, I think. Beginning of the 90s, I think.
Yeah.
They did some results. I don't know if he did almost surely on L2, but well, this prove L2, and then you can prove almost surely using Borel Cantel. It's not that.
So does the X play a role? So what does the X mean for your first inequality?
The X?
Yeah, so you have C of times B of X. So it's your
No, I just want to say that this function is bounded by B. So yes, I have a certain, this is almost surely starting from a certain X. And of course, this random variable depends on it. I fix my initial trait X, and my limit W depends on my initial trait. So how can you prove that this is just set T against F? So what I want to do is kind of project my process over the first eigenvector, the eigenspace, and look at the rest. So what I do is this I can decompose by adding and subtracting gamma A H, right? So this is like projecting over my first eigenspace, and this is the rest, the orthogonal part. And the good thing is that this, if I rescale it now like this, I have a martingale. So when I rescale, all this is converging to that limit. And what I need to prove is that this part goes to 0. So that's the main idea. And it's not that crazy, since this part is I'm projecting over the first eigenspace where I know that the eigenvalue is lambda, so I'm divided by exponential lambda t. And the rest should be what it's on the others eigenspaces, where the associated eigenvalue are smaller, because this is my principal eigenvalue. So the intuition should be that this goes to 0 when I rescale by exponential minus lambda t. This should grow as something exponential, at most exponential alpha t, where alpha is smaller than lambda. And again, since I have the second moment is just to say that this is a marginal converging in L2, so I have a limit, and the limit is not degenerate because, of course, the expectation is positive. If my eigenfunction is positive, yeah, it's the case. So just a little remark. You know that the limit is not degenerate, but in general, for this infinite dimensional process, you cannot say that the survival of the process it's equal almost surely to the limit being positive. I mean, you can have that your process grows, but when you rescale by lambda, that converges to 0 eventually. So meaning that every time in the finite dimensional case, whenever I want to say I'm conditional on the survival of the process, in this case, I'm a little restricted, and I need to say that I'm conditional on the limit to it. However, if I condition on this limit to be positive, I recover this law of large numbers, meaning that as in the finite dimensional case, not surprise, the proportion of the traits of the individuals when this process starts to grow. When I look at the limit, the asymptotic profile of this measure, this is a point measure, right? it's my eigenmeasure gamma. Okay. And again, I can ask, well, what are the fluctuations of these limits here, of this process around this limit node? So this question in the infinite dimensional setting that I show you has been answered before in some cases. So first, not that long ago in 2015, Adam Zak and Milos showed this in the case where this process, well, the process that I showed you at the beginning, all the dynamics of each trait is an Ornstein-Uhlenbeck process. All the branching is binary, so each time I have two new individuals. And the branching is local, so an individual dies, an Ornstein-Uhlenbeck is a branching Ornstein-Uhlenbeck process, but when it dies, it is replaced by two new particles in the same place. What is good there is that if I look at the spectrum of the generator, is well known, so I have a lot of spectral machinery to work that case. And in more recently, 2017, actually, it's a series of papers. There's three. I put the last one here that is the more complete. Ren, Song, and Chang, what they did is proof for a process where the dynamic of each in trait as a density with respect to the measure. In particular, I cannot allow deterministic dynamics. It's local, so I cannot have these jumps. And other hypotheses that I'm not gonna go into detail, but then ensure that your semigroup is compact, so I can like Jordanize. And I have access to the spectrum. And very, very recently, actually at the same time as we were doing, we discussed a lot with Emma Horton and Christopher Jean and Emma Horton, who worked also in the fluctuations of these kind of processes, but their assumptions are a little bit different than ours. But they have some stronger assumptions on the second eigenfunction. We have something on the first eigenfunction, they have something on the second, but I will tell you a little bit more about that result later. In all these three cases, what you have is three regimes of convergence. The idea again is I have access to my spectrum, so I want to decompose my process, and I'm going to look at the projections over each eigenspace, and I'm going to decide what are the fluctuations within that eigenspace. Depending on the eigenvalue that I'll be looking at, I have three possibilities. Two of them are Gaussian and one is not. So what we're gonna assume is that we have this Foster-Lyapunov criteria, but the speed of convergence is exponential. So my semigroup is stabilizing towards its eigenelements, and the speed at which this is going is exponentially fast. Of course, you can, if you have this for a certain row, you have this for a smaller row also. But the optimal row is the spectral gap. It's the distance between the principal eigenvalue and the rest of the spectrum. Under good assumptions, of course, of PT. But this was, I know there are other references when they prove exponential convergence, but I put these two, Champagnat-Monet for the studies of existence of quasi-stationary distributions, and Bansai, Chloé, Gabriel, Marguet for a model that's very similar to growth fragmentation. So let's assume I have exponential convergence toward.
This is equivalent to the
result.
No. To the equation, the infinitesimal equation.
Or the generator, yeah.
Yeah. This is equivalent, no?
Yeah. And we're gonna add a fourth moment, so I need to control things a little bit stronger, right? Because I will have convergence of the. I wanna have convergence of the variance towards something that I hope is Gaussian, so I need to control more than 2 moments. 3 moments, we couldn't do it with only 3 moments, so we say, okay, let's add 4 moments. And it worked. So first, let's see at the martingale part. So again, what I did is if I take any function f and I integrate it against my process, then this will have something times h plus this. So this, if I rescale it by the exponential, this is the martingale part. So I can decompose CTF for an F as the martingale part, plus something. If I call this f, say half f, that integrates 0 with respect to my eigenmeasure. So it's like in the orthogonal of the first type. So let's study it this one. Assume that I don't have that. And I have my martingale that it's convergence toward its limit w infinity. We can show is that this converge if I rescale by the size of the population, the square root of the size of the population. Then this is going to converge to a Gaussian random variable with a given variance. The variance is the limit of this variance, times the square root of w, where z is an independent random variable.
So you're assuming that gamma of h is like 1, right?
Yeah, of course. I never say that.
When did you assume that?
I didn't say it, but here. I mean, I have a Foster-Levin criteria for gamma and h. I know that there are eigen elements.
So h is in the okay.
Yeah.
Okay. Yeah.
So yes, I'm gonna assume all the time that they are normalized. So this is 1, and I can assume that that is 1 also. So here. So this is converging to this. There is a square root of w here, but the idea behind this is that actually that see h w infinity. If I divide by the square root of h, then this will converge to the sigma h. So I have this result. This implies this here because I multiply and divide by the exponential. This is just the square root of the martingale that is convergent to the square root of w infinity. So that implies this central limit term if I condition on the fact that w is positive. What is interesting is that we achieve a way to compute the distance between this fluctuation here, this process here, and its limit. And for the martingale, this is going exponentially fast. And the rate at which this is going depends on the eigenvalue and the speed of convergence of the stability of the semigroup. How much time do I have left?
Like 15, 20 minutes.
Okay, like this. So this distance is we consider this distance here. This distance implies the convergence in distribution, but it's just my test functions are functions that the function and the first three derivatives are bounded. And why do we do that? Is because to estimate this distance between this the speed of convergence in this distance, we use something that is called the Stein method. So what is this? Stein's method is a method that allows you, in this case, to compute the distance for a given distance that you like between a random variable and a Gaussian random variable. This later has been developed for almost any known distribution to compute these distances, but we're gonna compute the distance between a random variable y and a Gaussian random variable of variance sigma. So let's say I take a random variable, my variance sigma. So this is sigma z. What I'm gonna do is I wanna estimate this difference for a certain test function f that appears on this capital F. This is a set of test functions that I'm gonna fix later. If I can find another set of test functions such that I can always solve this problem given f find g, then I have that the distance induced by this family of functions is bounded by the superior. The idea here is this: if this is Gaussian, if y is actually Gaussian, this is true. You can prove that by computing this thing here. So Stein's method reduces to I have a set of the test functions. What is the good set of test functions that I have to put here so I can control this? If I know how to control this, then I can say something about the distance between these two things. Okay? So what do we do when aspire for this idea? The problem is that in this here, what I have in the limit is not Gaussian random variable. I have this square root of w that is bothering me. So what we're gonna do is, okay, let's say that I have the same thing, but instead of looking at set a random variable of variance sigma, I have a process sigma t, that is my variance that is evolving in time. But this process is adapted to my filtration of what I'm working on. And now I'm gonna solve this problem. It's the same idea here, but now my solution G, given a test function f, depends on t because I have fixed a sigma t here. But let's say that I can do this, then I can do the same here. So I take this. If I can once I take the supremum here, I can control it. It's not the direct, but I can control it. Then I can say something between the distance of the process of time t plus s and this thing here. So what is y in my model is just this here. So I can look at time t, condition on time t, use that is a branching process, so everything evolves independently, look at time t plus s, and try to control this thing here using the branching property. So now that I can control this, I can estimate the distance if I give a good space of test function f such that this is nice, I win. And the good space that we found to do that is the space of functions where the first, the function and the first three derivatives are bound. And that allows us to control this very well. And we have this exponential convergence. So what happens now if I take an f, not h? So this may not be zero, right? So what I want to do is, the idea is that this behaves like a classic central limit theorem. I have to rescale by the square root of the population, but this not necessarily, and it will depend on the value of rho. So in the finite dimensional case, it depends on the eigenvalue that I'm looking at. The only thing that tells me something about the rest of the space is the spectral gap, the distance between my principal eigenvalue and the rest of the spectrum. That is rho. Rho is also, remember, the rate at which my process is stabilized, my semigroup. So I have, with this method, with Stein method, we can prove two of the three regimes, which is not that surprising because we know the third regime is not Gaussian, and we're gonna use Stein method for Gaussian random variables. So if 2 rho is larger than lambda, remember that this is converging, is stabilizing at speed lambda, speed rho. So if this is going really fast, what is going to happen is that I'm not going to be bothered for the fluctuations at the other part of the space. What's going to win is the marginal part. So the limit is still Gaussian. And I have the same idea. I can compute the speed at which this is converging to my limit. If I'm in the critical point where 2 rho is equal to lambda.
Here, rho is really the spectral gap?
Yes.
It's the maximum.
Yeah. If 2 rho is equal to lambda, then we're in the critical case. What I'm going to see is that I start seeing and delimit these fluctuations here. What you can do is that you add a polynomial term to your change of scale. You are no longer going to see the marginal part because you know that this is converging as square root of exponential minus lambda t over 2, and you add a square root of t. So, but you're going to see something here. And that is still going to be Gaussian, but you have this polynomial term to see it. So the fluctuations are growing in the other directions, put it that way. However, we cannot estimate the speed. When you use Stein method, the only thing that you can prove is that the distance between this and this is bounded. So you have a constant. So a little bit of publicity. These two results, we put it in a paper that is already in archive if you want to take a look at it. So what happens with the third case? So what happens if this 2 times the spectral gap is smaller than lambda? And for that, I'm going to cite the work of Eva Horton and Christopher Dean. And what they did is that if you assume that you know your second eigenelements, and you have the same type of assumptions that for your first eigenelement. In particular, you assume that it's a simple eigenvalue, you have a unique eigenfunction H2. And the idea is that if I take the projection over the first eigenspace, then this is converging to something in the second eigenspace. Then you can recover the third case, there is the large branching case. And in this case, the fluctuations, you obtain a lower large numbers for the fluctuations. This converges to W2, the limit of your martingale. You look at the second eigenspace.
Nicolás, I don't know if, because it's very impressive what the theory of you have done, but for very simple things, not so simple, but I remember for multi-type branching process, when
Yes.
you saw a matrix, there is, I see an article of Kesten.
Kesten for the discrete time.
Yeah, where generalized different cases because
Yeah.
there is a problem with the matrix.
Yeah.
It has to do something with this.
Yeah. Kesten, what he does is this idea of projecting over every eigenspace. I have no access to all the spectrum here. So what I do is I just take this and I so the stability of this. But what he's doing is actually projecting over each eigenspace and see the fluctuation of each one, and then you have the three regimes depending if you're in the limit, you see what happens in that eigenspace because it depends on the difference between your eigenvalues.
More or less the same.
The idea is to generalize this for eigenvalues.
Okay, good. So many sense.
So the take-home message to finish.
But wait, is this kind of the complement of the other two regimes? Because there was no.
Under this extra assumption here. So
Okay.
if you change your Lyapunov criteria, no, actually no, because they have a similar assumption to your Lyapunov criteria for the first eigenvalue. And you add that you have the same for your second eigenvalue. What I think it's really strong is that you're assuming that your eigenfunction is a simple eigenvalue. So you don't have you need to have a unique eigenfunction, a unique eigenmeasure for your second eigenvalue. And if you have your stability in total variation, then you have the convergence, this law of large numbers.
So in principle,
And what happens, for instance, if you're in the finite dimensional case and your second eigenvalue is simple, you have this. If not, what you obtain here is you need to subtract the projection over all the eigenfunctions, but you have something that can oscillate. But this is the same result as the finite dimensional case. If you assume that your second eigenvalue is simple.
Okay.
And stability, of course. So the take-home message, so branching processes is a natural framework to study populations with random reproduction and structured populations. This structure leads us to see them as infinite dimensional processes, so it's point measures. And to analyze its stability, what we do is we use tools for the stability of the semigroup of PT, right? In this case, the Foster-Lyapunov criteria for non-conservative semigroups. The mean behaviors of the law of large numbers, this asymptotic profile of the population depends on the first eigenvalue, right? I divide by exponential minus lambda. I divide by exponential lambda t, and that converges to gamma fw. And the fluctuations around this limit depend on the spectral gap. Something that I didn't say before finishing. If you look, in this language, the case that I'm missing is 2 rho. This is not the good. 2 rho, I need smaller than lambda. But if you know lambda 1 and lambda 2, so lambda and the second eigenvalue rho is equal to lambda minus lambda 2 because it's your spectral gap. And so in your large branching case corresponds exactly to that. So the fluctuations depend in the three cases on the spectral gap. But in the large, at least for now, you need simple eigenvalue to say something in the large branching case. And the Stein method is not going to work because it's not Gaussian. You don't know the law of the limit. You know that it's just this W limit of the martingale in the second eigenspace.
But the use of this Stein method that you put that is quite generally,
Yeah,
it's appear It has appeared already in the
Yeah.
literature?
For this,
Yes.
for branching process, I've never seen it.
Okay,
So
good.
the speed of convergence of the fluctuations is something new. I think that I don't know if it's in the finite dimensional case, but not even in the Stein case is something new that we because we're using Stein's method that allows you to compute. Finally, well, this method provides a speed of convergence for the fluctuations for the martingale in the small branching case, and of course for the Gaussian case in the small here in the small branching case where you have a Gaussian limit, you can compute the speed. In the critical branching case, you cannot compute the speed, but you still have a Gaussian limit. Well, thank you very much.
Thank you, Nicolás. So are there any questions?
I have one question. On the critical case, you divide it as well by t or something like that? Yes,
Square root of
t. But it seems to me that if you, well, I don't know, but why isn't it true that if you divide by this term, like it's just annihilates the two main terms? So there are two leading terms, so one coming from the fluctuation. Yes, there is one, yes.
So in the critical phase, the fluctuations here are too large. So when you divide only by the exponential of lambda t to this, you cannot control these fluctations. You control the fluctations of this.
These are the orthogonal fluctuation. This is the orthogonal fluctuation or fluctuation?
Like orthogonal the fluctuations in the orthogonal space. That they're too large in the critical case. But your spectrum is too close to your principal eigenspace. The rest of the spectrum is too close to your principal eigenvalue. So you accumulate too much fluctuations here. If you divide by exponential lambda t over 2, this is Gaussian, but it will go to infinity. The fluctuations are going to win. So something that I can maybe say to give some intuition on why you divide these three cases is I want to compute something like this, right? Something like this up to an exponential change of variable. So what I'm going to do is I'm going to add the expectation of this. So this is a process that looks like the sum of, after you condition at a certain time, the sum of independent random variables, kind of, minus its expectation. So it should behave like the regular central limit theorem. Yes. So this should be like something like this. And this is your semigroup, and this is like your martingale. This is H, CPH. And you can control this with the Lyapunov criteria. So you have to compare lambda over 2 with rho.
Yes, but in the case where rho is lambda over 2, which is the critical case.
Yeah.
Why
this error here, it's you see it if you divide only by this.
Why is this much bigger? Why is this like a square root of t big?
Why is especially a square root of t? I tried to find an intuition. What you can do is that if you compute the variance of this,
okay,
like when you do the computation, naturally this appears that this is linear on t. So this is the second moment, so the process should behave like t, and it works. Why does it work? What is intuition? I am not sure.
Okay, but if I understood well, like somehow it's a very different Gaussian limits because it comes from the orthogonal fluctuation instead.
So if you look at the something important, the variance can be 0 here. This can be a degenerate Gaussian, and we cannot necessarily prove that this is. So it has a degenerate Gaussian here. Okay. So when you see something that is Gaussian, but maybe you kill all the fluctuations and the process and you go to 0.
Okay, but there are some f for which the sigma hat is not 0.
In the critical case, so should be the fluctuations here.
So it might be true that actually this is just saying.
Yeah, this could be true that this is going to 0.
Okay.
In this case. What we see for particular cases like the growth fragmentation process, at least in the simulations.
Okay.
There are cases where that does not go to 0, but just numerically we have proof. We have some cases. But in the small branching case, this is marginal, so this is strictly positive. So this is Gaussian all the time. There's not a degenerate Gaussian.
Okay. Well, I might be completely confused, but it seems to me quite surprising that this is going to a Gaussian. I mean, it's quite different in that nature.
Maybe, yeah. I don't know. I mean, I know that in the finite dimensional case, if your eigenvalues are close to your first eigenvalue, no, if they are far from your eigenvalue, you don't see it because
Yes.
you're divided. Your scaling is something too big, so your fluctuations do not win. That's the idea.
Yes,
That's why you have this condition. So your fluctuations are really far.
Yeah, the bonus condition, besides the fact that you use it and you get some exponential convergence to something at the limit. Are you using it explicitly or any? I mean, do we have any other condition giving you some exponential convergence of the semi?
If I'm using the fact that it's exponential,
No. I know I understand that you're using it, but you don't need the Lyapunov condition to ensure that maybe. I mean, do you really?
I mean,
or do you use the
yeah. I
Lyapunov
mean,
condition besides that.
you mean if I can only assume that I have stability of the semigroup?
By Lyapunov or
By Lyapunov or another method?
other-
Yeah, I mean, I use this method because
It's available and it works.
yeah, it's available, it works, but also give you a simple eigenfunction, and you don't need to verify many high assumptions. I don't even know if the eigenfunction is continuous, for example. Like I will need to add too much regularity on the semigroup if I want to use another method, because usually other methods give you some regularity on the eigenfunction or something like that. Here I only know that the eigenfunction is bounded by B, and that's because I have just mild assumptions on the semigroup.
But you just use it. You don't use it for something else besides granting the exponential
Stabilization, exponential activization, and simple eigenfunction.
Yeah.
And that there are not very hard to verify assumptions on.
Yeah.
Only that.
No, it's very impressive that it works.
Yeah.
I have one question. So, what happens if you, like, for example, know H and H is nice, and you know gamma and gamma is also nice, and okay, you can kind of quantify the convergence, like the stability, but gamma of H is not finite. And
At least with the Lyapunov criteria, I'm ensuring that gamma is a function that integrates P.
yes, but what happens if you don't have? So if yeah, so like maybe you have a nice H and a nice gamma, but
so I will, if H doesn't, maybe when you use your law of large numbers, I don't know if you will see some asymptotic profile, like you will obtain something that doesn't integrate H also in your limit, and in that case, I don't know if you will have your.
So there are some branching Brownian motion type models in which gamma of H is infinite.
Yeah.
But you still have a law of large numbers.
Okay.
And you have a very good information of what H and gamma are and the speed of convergence.
Actually, I don't know, but it's a very good question. In this case, we all the time use that you can integrate H, of course, you know. But I don't know what would happen if.
So I guess this is maybe related to Joaquin's question. Like, if you more or less know, you can like.
Yeah. For some of the reasons you know that the stability exponential. Yeah, I don't know.
That's it.
Are there any further questions in the chat? Which it feels like we're the same. If not, let's
Excellent.